Namaste. Let us start the next lecture of week 11. In this week, we are talking about the characterization techniques which are used to characterize the nanomaterials. In the first lecture, I gave you a broad overview about some of the techniques out of the large number of techniques which are required or used to characterize nanomaterials. In today's lecture, let us start and discuss some of the specifics, and today we would like to talk to you about some of the techniques more in detail, namely XRD, TM and some kind of light scattering based techniques. Nanomaterials. What did we discuss when we were talking about nanomaterials? If there are 3 dimensions, then we talked about that we should have these materials in a way that the dimensions either x, y or z, 2 of them or all 3 sides are in the range of 1 to 100 nanometers. So, the whole definition is based on the size. Therefore, we should start our discussions to find out the particle size of the particles which are being synthesized. Obviously, we are talking about nanometric range. So, you cannot use your normal scale to measure these dimensions. So, obviously, you will have some other techniques to carry out the particle size analysis. We have seen both in nearly free electron model or quantum mechanical formulation of nano systems, more so particles, using particle in a box problem, that the size of the particle plays the predominant role in determining the optical, electrical, thermal and to an extent the mechanical properties of these particles. One of the most commonly used techniques for determining the grain size, the crystallite size, or if you are talking about very low dimensions, then we call it as particle size, is the technique of X-ray diffraction. We had talked about this briefly in the first lecture of this week. So, let us spend some more time. So, let us spend some more time in understanding the way the crystallite size or particle size can be estimated using an X-ray diffraction data. So, when you take an X-ray diffraction pattern, you can get diffraction profiles and you can get profiles for composites or mixtures. You can get highly crystalline peaks which are much sharper, and when you go to small sizes, there is the broadening of the peaks which are observed. Now, from here you have 2 theta versus in intensity curve. How will I determine the crystallite size? This is the question which will come to your mind, and this was solved by Scherrer, and the equation which is used to determine the crystallite size is called the Scherrer equation. Please note that Scherrer equation was written by believing that the particle had shapes which were similar to spheres. So, spherical particles, but not always do you see that it is spherical shaped particles, and therefore, to account for the changes or correction factors which needs to be introduced to move from spherical particles to other morphologies, there is a correction factor which is used. But the Scherrer equation is generally written as d is equal to k lambda divided by beta cos theta, where d is the mean size of the crystallite domain, k is a dimensionless factor with a typical value of 0.9, but this can change with the shape of the crystallites. Lambda is the wavelength of X-ray which is incident on the sample. Beta is the broadening at half maxima, which is called as full width at half maxima. So, if there is a peak, let us say 001, then this is the maximum, and this is only the peak coming in from k alpha 1, then you take the half of this and then you find out what is the width. So, this is let us say theta 1, this is theta 2, and FWHM is theta 2 minus theta 1. So, this is what you have. So, clearly you can see the FWHM varies as we move from one system to the other, and theta is the Bragg angle, the angle at which the peak profile is observed. It can be here, it can be here, it can be here, it can be here. So, corresponding theta, this is 2 theta, and from there you can get the theta value. So, this is what you have. So, for example, if you take the ZIF systems, these systems can be used to find the particle size. We will understand these things in a minute. So, for example, you have the ZIF, which stands for zeolitic imidazole framework like structures, which are like deposited or grown on carbon nanospheres or reduced graphene oxide or pure ZIF 67, which is a cobalt based interlinked system. Now, you can see that the nature of the curves are changing. So, along with that FWHM is changing and intensity is normalized in the 3 cases. So, if you find out, then you will see that the crystallite size in the 3 systems are different. You can go from around 40 nanometers to around 48 meters. You can see the FWHMs are different, and that gives you the indication about the changing particle or crystallite size. So, let us go back and see what we have started. So, this is where we have understood the Scherr equation. So, you collect the intensity versus 2 theta curve. You take the powder, put it on the sample holder, you have an incident beam and the detector moves in the 2 theta circle. So, you have theta 2 theta movement and you get the value of 2 theta at which the peaks are appearing. Then you index them, assign the Miller planes to the peaks which are giving these diffraction conditions. So, 2d HKL sin theta is equal to lambda or 2d sin theta is equal to n lambda. So, as HKL changes, you have different thetas which will satisfy this condition. So, now you see that there is peak profiles, you have indexed it, and next you calculate the FWHM. So, for example, this is pure ZIF 67. So, you take the maxima, go to nearly the half and find out the FWHM, which is around 0.166 degrees in this case. D is equal to 0.9, fine. Lambda, if we take copper K alpha, then copper K alpha 1 has 1.5406 angstrom as the wavelength. Peak position, this position corresponds to approximately 7.2 degrees. Theta, this is 2 theta. So, theta becomes 3.6 degrees. Cos of 3.6 is given by 0.99802673. So, you can either truncate it at certain point or you can take this value. FWHM is 0.166 degrees. Then you convert it to radians. So, that becomes this value into pi by 180, that gives you 0.002897 radians. So, crystallite size becomes 0.9 into 1.5406 into 10 raised to the minus 10 meter. So, we are talking in terms of meter. Beta is coming in from here. This is the value for cos theta. Do the mathematics and you will get the value of the crystallite size from which the diffraction is taking place. So, if you go back, then you will find that the peak, as you move from one peak to the other, then the broadening may change. So, what generally it is done that you take the singlet peaks, for example, 002 or so, 001, 100, and use its FWHM to find out the crystallite size. Else you must mention the crystallite size which have been calculated corresponding to the Miller indices of the peak profile which was used. And then you can do it for all the samples and you can easily calculate the crystallite size. So, this is as simple as this to find out the crystallite size using X-ray diffraction technique, and this is one of the most common ways in which it is done. Then you can compare it with other techniques also. You have transmission electron microscope. For example, this is in gold particles in between the tin oxide flakes. So, you can see the flake like structures of SnO2 in between which the gold nanoparticles are dispersed, and using this scale you can find out what would be the size of the flakes and the particles which are dispersed. You can even find out the polymer matrix and the size of the polyaniline nanoparticles which are dispersed in this material. So, it is also a very easy technique. Then comes the light scattering methods. This is carried out by analyzing how the particles scatter the incident light, and the extent of scattering depends on the particle size, the incident wavelength, and the polarization of the incident beam. If you look into the Rayleigh-Gans theory, then you will find that when the particle to diameter wavelength ratio is less than 0.1, it gives a situation which is suitable for nanoparticles to be measured using optical wavelengths. So, laser beam scattering can be used and has been used to show organic solvent dispersions which have particles in the size ranging from 9 to 30 nanometers and peaking around 12 nanometer. This method is effective for particles down up to 2 nanometers. What happens? DLS is based on Brownian motion. From the principle of Brownian motion, we know that there is a random motion if small particles are suspended in a liquid, and the corresponding Stokes-Einstein equation is given by dH is equal to k beta t divided by 3 pi eta dt, where dH is the hydrodynamic diameter, Kb is the Boltzmann constant, T is the absolute temperature, eta is the viscosity of the medium, and dt is the translational diffusion coefficient. Now, when you have a sample where these particles are dispersed in a liquid media, you have the incident laser. These lasers, when they hit the particles, they get scattered. Now, the intensity of the scattered light will fluctuate because these particles are continuously moving and showing a Brownian motion. These fluctuations are faster for smaller particles and slower for larger particles. So, you see these kind of intensity versus time curve. Then, if you can draw the corresponding correlation functions as a function of time, you will get the correlation function, and this is called autocorrelation. What will happen? The fluctuations are basically monitored by taking rapid snapshots and comparing it with the original signal. So, you have a comparison and that gives you an autocorrelation. So, the rate at which the signal similarity is lost, that is the correlation decay, directly corresponds to the particle size. So, it is as simple as this. Now, the diffusion coefficient derived from the autocorrelation function are then used in Stokes-Einstein equation, and you can calculate the hydrodynamic size of the particles. And in the case of sphere, you will find you will have the cases where there will be diffusion at the same rate as the particle, including any bound surface molecules. It is basically an optical setup where you have a laser, that is monochromatic coherent light source, and scattered light is detected, often in backscattered configuration, so that you have efficient detection even at low concentrations. Then you can use the homodyne detection, or you can use heterodyne detection, where you have mixes of scattered light with a portion of incident light. This results in a stronger and more accurate signals. Once you have the autocorrelation function, which is also known as photon correlation spectroscopy, you can either use this process or convert the signal via Fourier transformation into frequency power spectrum FPS, and the characteristic frequency then relates directly to the particle size. And the average Z is often reported along with the polydispersity index to indicate samples heterogeneity. If you look into the DLS measurements, you will find it can measure the hydrodynamic diameter. Its accuracy depends obviously on temperature and viscosity, and you have up to a range in which DLS can give you reasonably high quality data, but it can work across wide concentration range, meaning from ppm to around 40% dispersion concentration, and can also support in situ or probe based measurements. As you see, there are some limitations in this. What is that? If you have a highly polydispersed sample, you can get misleading results, because you do not have same size particles. Some are small, some are larger, and then it varies from one part to the other. So, continuously you may end up getting different types of data, and you may not be able to get the true picture. Presence of larger size particles or aggregates can obviously distort the signal, while the high concentration may include multiple scattering, leading to inaccurate size readings. So, you have to optimize the concentration at which you will get the best data. You have to ensure that polydispersity is controlled, and you must ensure that the suspensions are not aggregating. If you want to go to even smaller size particles, then the techniques which are used are mass spectroscopy. So, what do? You have nanoparticles which are ionized by the impact of the electrons which are coming out from a heated element in the ionization chamber. So, you have the electrons which are emitted, and then they hit the sample, and then you collect the ions which are coming out from the sample. So, the newly formed ions are accelerated through the potential V between the repeller R and accelerator A plates. Ions are focused by lenses L and collimated by slits S before entering the mass analyzer. Inside the analyzer, you use a magnetic field which will exert the force Q VB on the moving ions. Why? Because we are considering magnetic field B, which is oriented normal to the page. So, you get F is equal to Q VB from the Lorentz force. This will bend the beam into the circular path of radius R, that is 90 degrees deflection, and these ions are then detected at the ion collector, and the M by Q ratio can be determined using the relation given here. Now, either the magnetic field B or accelerating voltage V is varied to focus ions of different masses at the detector, and the charge Q of the nano sized ions is generally known, because we know that there is a material which has certain elements in it. Hence, the measured parameter is the mass m of the ion. If the density rho is known, then what can be said? Size to diameter can be estimated as the cube root of volume, which is d is equal to v under root 3, that is v cube root, and that is m by rho raised to the power of 1 by 3, and you can get the estimate of the size and diameter. The described instrument which we discussed is the magnetic field mass analyzer, but you can have spectrometers which are quadrupole analyzers or time of flight analyzers. In TOFs, ions gain the same energy, that is half mv square. Lighter ions will move faster and reach the detector earlier, and heavier ions will arrive later, and this provides separation of ions by mass. So, I hope now you have understood more clearly the use of some techniques to determine the size of the particles, the nanoparticle composition, and how you can also investigate the shape of the particles or homogeneity in a system which has been fabricated. These are some of the references which are useful and can be referred to for understanding the topics discussed today, and I thank you for attending the second lecture of week 11. Thank you very much.